Serializers and deserializers. It sounds simple enough. You just convert parallel data to serial, pipe it over some kind of cable, and convert the serial data back to parallel. Easy peasy. But as we've seen, it's really not that simple. Maybe the problem is the name. A serializer is really much more than just a parallel to serial converter, and a deserializer is much more than just a serial to parallel converter. There's a lot more logic in there than just a shift register. Maybe an analogy is in order. Think of the high-speed GMSL line as a truck. At the serializer, you have a whole crew to disassemble the incoming video, carefully pack it into padded boxes, label the boxes, and stack them in perfect order into the truck, and then send it on its way. At the deserializer, you have another crew that unloads the truck, unpacks the boxes, carefully reassembles the video, and presents it as a video stream just like the one that came into the serializer. Now, when you look at it that way, you get a little more respect for the job that the serializer-deserializer pair has to do. And it all starts with the crew that takes the video stream from the source and disassembles it into its component pieces, and it ends with a crew that receives the component pieces and reassembles them back into a cogent video stream. Hey, it's not a trivial job. To understand the job these tireless workers perform, we're going to take a look at some real-world interfaces that represent connections you're likely to encounter. We'll start with a legacy interface to draw a baseline, and then we'll look at a camera interface, a few display interfaces, and finally the interface to video players. Representing legacy interfaces, pure parallel. Representing camera interfaces, MIPI CSI2. Representing display interfaces, we'll look at MIPI DSI, OLDI, and embedded DisplayPort. And representing video player interfaces, we'll look at HDMI. That's a lot of material to cover, so let's get going. We're going to start with parallel. Parallel interfaces are a convenient baseline. They're conceptually simple, and they're pretty familiar to those who've been using displays and cameras. Let's see how they work. By convention, pixels in a parallel interface display or camera are scanned left to right and then top to bottom. Each pixel is expressed on a parallel bus. Now, frequently the bus will be divided into the three primary colors, red, blue, and green, but it's possible that the camera or the display might use a different color space. A clock signal indicates when a new pixel is ready on the bus. At the end of each row and at the end of each frame, there's a delay. In the days of cathode ray tubes, this delay allowed the electron beam to snap back to the beginning of the line or to the top of the frame. But these days, that delay is there to give the digital logic time to load or store the data and to send an end-of-line or end-of-frame packet. Two wires, a horizontal sync line and a vertical sync line, signal the beginning of a new line or the beginning of a new frame, respectively. A third line, display enable, indicates when the data on the bus is presenting valid pixel data within the visible portion of the video field. The display enable signal should persist for precisely the number of pixel clocks as there are active pixels in a row. And at the end of the frame, there will be rows without a display enable active period. The display enable signal lets the receiver know exactly when active pixel data is actually available. Now, have you noticed any, let's call it redundancy? Notice that the display enable signal looks an awful lot like the inverse of the horizontal sync signal. Well, you're right. Lots of camera modules don't include a display enable signal. They just provide horizontal sync and vertical sync. And many display modules don't really need the horizontal sync. They just need the display enable signal and a vertical sync signal. And for that matter, vertical sync can be synthesized by noting when the display enable signal is inactive for a long time. The lesson here is that while all three signals are significant, not every one of them are used in every application. Okay, that's parallel. It's simple, clean, easy to understand. Now let's turn our attention to CSI2. CSI, the Camera Serial Interface, is a set of standards governed by the Mobile Industry Processor Interface, or MIPI, Alliance. CSI2, the current interface standard, is a faster and more flexible standard than CSI1. The CSI2 standard is currently at version 3.0 as of 2019. Now, CSI2 really defines two separate communication paths. One is a unidirectional path from a CSI2 transmitter, like a camera, to a CSI2 receiver that you might find in the electronics control module of a vehicle. The other path is for control signals. The ECM uses this path to set the camera's operating parameters and get the status from the camera. Now, describing that control path is really easy. It's most often just I2C, although MIPI has defined a faster interface based partly on the principles used in I2C called I3C. It's the main video path that's kind of interesting. First, understand that the CSI2 video path is not parallel. It's kind of a multi-lane serial arrangement. Each lane carries a portion of the pixel data, just transmitted serially. Well, simple, you might think. It's just like parallel, except we serialize the lanes to reduce the number of lines from the camera to the serializer, right? Well, no, not even close. CSI2 is a complete protocol of its own, running on a physical layer that may be one of two distinct types, called DPHY and CPHY. Now, DPHY is the more conventional. Each lane is a differential pair, and there's a separate differential pair that carries the clock signal. The clock signal is not actually a pixel clock, it's a half-rate bit clock. On each edge of the differential clock signal, the state of each data line must be sampled by the receiver. The differential clock plus the set of differential lanes make up the DPHY interface. CPHY is more complex. There is no independent clock lane. Instead, the clock is derived from the transitions on the data lanes. And the data lanes aren't strictly speaking differential. Each data lane is composed of 3 wires, not 2. The coding on the 3 wires of each lane makes data transmission a little more than twice as efficient compared to the DPHY, but at the cost of some pretty significant complexity. And by the way, the D in DPHY doesn't stand for differential. Originally, the thought was that the data lanes might support 500 megabits per second, and D is the Roman numeral for 500. Later revisions of the specification extended the speed to several gigabits per second per lane, but the D designation stands. The C in CPHY stands for constrained channels. The thought was that if the lane count were constrained, then there'd be a need to increase the number of bits per lane, so now you know. So how many lanes are needed? Well, that depends on how much data you need to send and how quickly you need to send it. A 1080p high-definition signal running at 30 frames per second with 24-bit pixels requires about 1.5 gigabits per second, not counting blanking intervals and overhead. So let's say you'll need 2 to 2.5 gigabits per second. Now, you could transmit that signal over a single lane if you wanted, or split the signal over, let's say, 3 lanes, with each lane running at about 700 megabits per second. And keep in mind that this is a conservative example. Both cameras and displays are frequently quite a bit bigger than the HD example given here. And while 30 frames per second is common for cameras, displays most often operate at 60 frames per second. In any of these cases, the CSI2 standard defines how to pack the pixels into bytes and how to distribute the bytes among the data lanes. When they're not in use, lanes in a CSI2 interface rest in a low-power idle state. But when there's picture data to be transmitted, they spring to life and carry the image data in packets, 1 packet per line of video. At the end of each line, that is, during the horizontal retrace interval, the data lane reverts back to its idle low-power state. After the last line of a frame has been sent, a CSI2 transmitter sends an end-of-frame packet and sets the data lines to their low-power idle state. This marks the beginning of the vertical retrace interval. When the camera is ready to send the next frame, it sends a start-of-frame packet and then begins sending picture data, once again, one line at a time. Now, there's a lot more to CSI2, but that gives you an idea. It's a multi-lane, packet-based mechanism to connect a video source, most frequently a camera, to a device that needs the video stream. Now, displays. In the not-too-distant past, a display would interface over a set of parallel wires, but other than for the smallest displays, that's just no longer true. Today, virtually all display subsystems connect over some kind of multi-lane serial interface. Three of the most popular are DSI, OLDI, and EDP. We'll start with DSI. It's a lot like the CSI2 interface. Both are governed by the MIPI Alliance, and in fact, DSI and CSI2 use the same physical layers, either the DPHY or CPHY that we just covered. DSI includes a few features that make it more suitable for display interconnection. For example, you can assign video streams to multiple displays, but for our purposes, if you understand CSI, well, you also understand DSI. Alright, now let's look at OLDI. It's a display interface. The letters stand for Open LVDS Display Interface. And yes, the physical layer is based on well-known LVDS levels. Now, in fact, you'll often hear engineers talk about an LVDS video interface. Well, that's OLDI. Compared to CSI2, OLDI is really simple. Once again, you have a differential clock and a collection of differential lanes. Each lane carries exactly 7 bits per pixel. In the OLDI specification, there's a fairly limited number of arrangements of lanes. To start, you can have 3 lanes carrying 6 bits per color, plus 1 bit each for horizontal sync, vertical sync, and display enable. For more color depth, you can add a 4th lane that adds 2 bits to the depth of each primary color. The 7th bit in the lane is reserved. Alternately, you can specify either 6 or 8 lanes that carry 2 pixels of 6 or 8 bits per color to allow for higher pixel rates. Simple. The clock in an OLDI system is truly a pixel clock. The clock is in the active state for exactly 4-bit times and in the inactive state for exactly 3-bit times. And each pixel starts at the midpoint of the active state. Synchronization information is carried in every pixel, so it can be easily recovered in the OLDI receiver. The sequence of bits on the data lanes is defined in the specifications, one way in the OLDI specification and slightly different in the VISA specification. Now, it's not nearly as simple as a red lane, a blue lane, and a green lane, but that's okay. The logic in the receiver can easily move the bits to where they need to be. The last display interface we'll consider is EDP. That's Embedded DisplayPort, and yes, it's the embedded version of DisplayPort that you may have used to connect your computer to a monitor. DisplayPort uses multiple serial lanes just like DSI and OLDI, 4 high-speed serial lanes with an embedded clock, and an additional auxiliary channel. Each lane can run at one of 4 possible speeds: reduced bit rate, high bit rate, HBR2, or HBR3. And later versions of the DisplayPort specification allow operation up to nearly 80 gigabits per second. Embedded DisplayPort takes advantage of the physical layer characteristics of DisplayPort, but it tailors the interface for embedded applications. That means you can have 1, 2, or 4 serial lanes that operate at any of the supported speeds, so long as the driver chip and the display support the same EDP version. And because the DisplayPort protocols are packet-based, Well, there's no worry that the link is running too fast. So long as there is sufficient bandwidth, EDP will get the picture through. Our last interface type is one that you're probably already familiar with, HDMI. HDMI, the high-definition multimedia interface, was developed to connect video players with display units, most often an HD TV. But in an automotive environment, HDMI most frequently connects a video player to the electronics control module, and that presents some interesting issues. See, HDMI was originally developed to fulfill two major objectives. First, with the advent of DVD and digital cable and satellite TV and even digital over-the-air programming, the industry really needed an all-digital mechanism to connect a video source to a display. And second, given the rampant piracy seen in the videocassette era, they needed a way to protect the content of the video stream from copying. The solution was HDMI. To start, let's tear apart an HDMI cable and take a peek at what's inside. Inside an HDMI cable, you'll find 4 sets of shielded twisted pair, with each shield independently terminated on the connector. That's 12 connections. The 4 sets make up 3 data lanes and 1 differential clock. There's a separate system ground and a 5-volt power circuit, so it's possible to provide a small amount of power to whatever device is receiving the HDMI signal. There's one line called CEC. That stands for Consumer Electronics Control. Now, its job is just to relay communications from remote control devices. For instance, volume down to a TV set might be relayed to a sound bar. There's a pair of wires that alternately are used for hot plug detection, reverse channel audio, and a 100 megabit Ethernet link, depending on the exact implementation. And then there's one more pair of wires, the Display Data Channel, or DDC. Like the Camera Control Interface channel in CSI2, it's based on the I2C physical protocol. The DDC tells the HDMI source what kind of display is attached and what it can do. Its resolution, color depth, color model, refresh rate, and other information. And it's also used as the basis for the content protection scheme, and we're going to look at that in just a moment. Like CSI2 and OLDI, HDMI uses a set of data lanes plus a separate clock to convey the video data. In HDMI, there are 3 lanes. They're called channels in the HDMI literature, and each channel carries 10 bits per pixel clock. Now, those 30 bits could carry 24 bits of video data, or 12 bits of auxiliary data, like an audio stream, or 2 bits of control information, like the horizontal and vertical synchronization signals. Now, it would really be nice if I could tell you that the blue pixels go in this time slot and the right channel audio samples go in that time slot. But because HDMI is so flexible, it's impossible to universally specify where everything goes. Just suffice to say that a serializer with an HDMI interface can decode the stream, extract the audio and the video information, and get the recovered streams ready for the serializer stage. But remember, one of the objectives of HDMI was to protect the video stream from unauthorized copying. And to do that, the HDMI forum turned to a system originally designed by Intel, called HDCP, High Bandwidth Digital Content Protection. The idea is this: before any kind of protected content is transmitted from one device to another, 3 things have to happen. First, the receiving device has to be authenticated. Is that device authorized to receive and decode the protected content? Second, it has to be determined that the sending device and the receiving device are in reasonably close proximity to one another. No transmitting protected video streams halfway around the world. And third, the content must be encrypted using a key that's known to both the transmitter and the receiver. And that means the transmitter and the receiver must agree on a shared key. The transmitter will use the shared key to encrypt the session key that in turn encrypts the program information. Now, I'm telling you about all this because many of Maxim's GMSL serializers and deserializers include an HDCP block. If you're going to be handling video streams from protected sources, like a Blu-ray player, you'll need to plan for HDCP. Maxim has HDCP-enabled GMSL serializers and deserializers with a variety of input and output interface technologies, so you might have a video player with an HDMI output on one end of the serial link and a display with an LVDS input on the other end, with the channel protected all the way with HDCP. Now you see how interfaces actually work. But there's a lot more to tell. Stay tuned for more about Maxim's GMSL serializers and deserializers.